Hello, today we will discuss Euler's theorem, which tells us that if we are given any positive integer n and number a which is coprime to n, a to the phi power must be equal to 1 mod n. And what is phi n? Phi n is the number of integers which are coprime to n, and I must be between 1 and n, and GCD of I and n must be equal 1, and GCD of a and n must be also 1. It's clear that otherwise we will not have any power of a which will give us 1 mod n. Now let's discuss the numbers which are less than n and they are coprime to n. Call these numbers a1, a2 up to a phi n, because in total we have phi n numbers. And now let's discuss the numbers. A times a1, a times a2, up to a times a phi n. This is index. Okay. Now we will show that these both numbers must be permutation of each other modulo n. All these phi n numbers must be permutation of each other modulo n. It's clear that if a is coprime to n, all of these numbers, a times a1, a times a2, a times a phi n, must be also coprime to n. And now we will show that each of them will have different remainder modulo n. So let's discuss that a times ai equals a times aj modulo n. This is a contradiction of our statement. And what will we get? What will we get in this case is that a times ai minus aj equals 0 mod n, because we know that a is not divisible by n, and even it is coprime to n, but then we can erase the a. So ai minus aj equals 0 mod n. And clearly this is impossible because absolute value of ai and aj must be, both of these numbers are less than n, so their difference must be also less than n, and they are not equal to each other. So this is impossible, and every numbers in this set will give us different remainder modulo n, and all of them must be also coprime. So finally we got phi n numbers which are coprime to n, and they don't have any common remainder modulo n. So this means that these two permutations must be also same. Now we will use the same trick which we have used for the Fermat's theorem. Let's take a product in the first set, a1 times a2 times up to a phi n. This must be equal a to the phi n power times a1 times a2 times up to a phi n modulo n, because of these numbers are equal modulo n. So their product will be also same. We can erase these numbers a1, a2 up to a phi n in both sides, because we know that they are coprime to n, and both of these sides have the same numbers like this one. So we get that 1 equals a to the phi n modulo n. So this was what we wanted to prove. Now we can check this for the case of prime numbers. If n is prime, phi of p equals p minus 1, and in this case we will get Fermat's little theorem, which is also correct. So we have concluded that the Fermat's little theorem is the only small case of the Euler's theorem. So we have proved much more harder than Fermat's little theorem. If you want to discuss some theorems, please write in the comments.